So as we start into section 2.6, we start working a lot with composite functions. And the composite function is basically functions of functions. Basically, it's whenever I take the output of one function and use it as the input of another. So a very common way it's often represented is to say here, I'm going to do f of g of x. So as an example, if we let f of x equal x squared and g of x equal 4 minus x, we want to find the function f of g of x. So to do that, I would first, start from the inside and work my way out. G of x is simply 4 minus x, so I'm going to replace the g of x with 4 minus x. Now, f of 4 minus x tells me I'm going to go to the function f of x and replace every x with 4 minus x. So I would end up with 4 minus x quantity squared. Now you could actually leave it like that, but sometimes you might want to simplify it or expand it in this case. So if I did that and took it a step further, I would say that f of g of x could also be written as 16 minus 8x plus x squared. Again, it's going to really depend on the circumstance you have. This one would be simpler to do this way when we start doing other things with it, namely the chain rule, which is coming in the next couple of examples. So essentially when we see this kind of notation, I'm taking f of x in this case, which was x squared, with x replaced by whatever g of x was, which was 4 minus x. So that's how we do it. So now it's your turn. You try to do the same. So for your turn, your example, you were given that f of x was equal to x to the fourth minus 3x squared plus 8, and that g of x was equal to the square root of 2x. So again, you were asked to find f of g of x. Always be aware of what order that they have to have the functions coming in, because sometimes you might be asked for g of f of x, or they might have other letters for the functions. You always want to pay attention to that as well. But if I'm going to do f of g of x, again, I'm going to replace g of x with what it is. So that's going to be, so the g of x is being replaced with the square root of 2x. And now I'm going to go to the function f and replace every x with the square root of 2x. So I'm going to have the square root of 2x quantity to the fourth power minus 3 times the square root of 2x to quantity to the squared power plus 8. Now, when I take fourth powers and square roots, that will get rid of the radical. In the case of the first one, I'm going to end up with the quantity, basically 2 squared times x squared, or basically the quantity 2x squared. The square root of 2x squared is just going to be 2x, and of course the plus 8 just kind of keeps going along for the ride. So I'm going to end up with 4x squared minus 6x plus 8 as being the function f of g of x. Now, an important skill that we're going to be utilizing as we make use of the chain rule is to be able to decompose a function so that I could properly use the chain rule. So here, here we're being asked that we have h of x, which we're being told is the result of f of x and g of x being composed as f of g of x. So what we want to do is determine some f of x and g of x functions that would become this function whenever I would compose them in that order. Now, the fact of the matter is, when they ask you a question like this, there's often more than one answer that you could give. There's a whole bunch of them you could probably give, and I'm going to show a few of them in a moment here. Ultimately, though, you'd like to be able to show that whatever you pick, whenever you compose it again, when you have your f of x and g of x and do f of g of x, you get back to the original function. So, so some of them, I think I have like 6 of them here, so let's kind of show them. One thing I could do is say, like, well, if f of x is the fourth root of x cubed plus 5 and g of x is x minus 3, you can see that, if I do f of g of x, I'd replace that x with the x minus 3, and I would end up with what h of x is. Another thing I could do is say that f of x is the fourth root of x, and then say g of x is everything that's underneath of the radical, namely the x minus 3 cubed plus 5. That would be another feasible solution for that one. I could also say that f of x is the fourth root of x plus 5, Oh, this one doesn't seem to work out. I think I did forget something on this one. So, yeah, this one here, yeah, this one here should actually be, I think I got ahead of myself when I was writing this. This should actually be x minus 3 cubed, because that's what I need to replace x with to get to the function that we have over there. So, um, another option, if f of x equals x squared, I could say that g of x is the 8th root of x minus 3 cubed plus 5. Because all I would do in that case is that I would be squaring an 8th root. And since we know an 8th root is the 1/8 power, multiplying that by 2 would be a 1/4 power. And a 1/4 power is, of course, the 4th root I see above. F of x could also be the 4th root of x minus 1. And I could have g of x be x minus 3 cubed plus 6. Because basically, if I replace x with all of this, I would have x minus 3 cubed plus 6 minus 1, which would give me the plus 5. Or, of course, I could go to really, really cheap route and just say, well, you know, f of x could be the same thing as h of x, and g of x is just x. As I said, this is kind of, you know, pushing it, you know, because it's not kind of that's not the spirit of the problem, but it's not incorrect either. Most of the time, you might be asked to determine if these two functions are a decomposition of another function, and that's more along the lines of what you're going to be asked in the example I'm going to give to you. So here is your turn to try to answer a question involving decomposing a function. So you were given j of x is equal to the square root of x minus 3 all over the square root of x plus 3. And you were told that j of x was equal to g of f of x. So here we kind of reversed the replacement of the g and the f. So the f of x is going to be applied first, and then that's going to be plugged into g of x to end up with whatever j of x is. And so we're looking to see which of these 6 would be a good decomposition of j of x. And the best way of doing that is to basically try them out and see if I do g of f of x, do I get the same thing as j of x? So when I look at the first one we have here, when I do g of f of x, that's the same thing as g of the square root of x, and I end up with the square root of x minus 3, with the minus 3 outside of the radical, and I end up with the square root of x plus 3, again with the plus 3 outside the radical. These are not the same thing. Sometimes students mistake them for being the same thing, but they are not the same thing. So as a result, this would not work. G of f of x, I mean, if f of x is just x and g of x is the same thing as j of x, obviously, you know, trying to see here. Yeah, that's not correct. This should just be an x here. I think I was doing some cutting and pasting. That should just be x, because this is just going to be g of x, because that's all f of x is. And I would end up with the same thing, so this is a valid way of handling it. For the next option, f of x equals x plus 3, and g of x equals the square root of x minus 6 over the square root of x. If I replace f of x with x plus 3 and then go into g of x and replace all the x's with that x plus 3, I went up with x plus 3 minus 6 on top underneath the square root, and the square root of x plus 3 on the bottom, which ends up being the square root of x minus 3 over the square root of x plus 3. So that's the same thing. For f of x equaling x minus 3 over x plus 3, and g of x equaling the square root of x. In this case here, I am replacing f of x again with x minus 3 over x plus 3, which gives me the square root of x minus 3 over x plus 3 all underneath the same radical. But if I square root a fraction, it's like me square rooting the top and bottom separately. So I can separate that into two different radical expressions. You know, have one in the numerator, one in the denominator, because those are the same thing. So this case here, g of f of x is the same thing as j of x. For f of x equaling the square root of x minus 3 and g of x equaling x over x plus 6, when I substitute in the square root of x minus 3 in for, you know, all the x's, I end up with the square root of x minus 3 on top, but on the bottom I end up with the square root of x minus 3 with a plus 6 on the outside, and that is not the same thing. I can't combine the minus 3 and the plus 6 when the addition of 6 is occurring outside the radical. So this is not the same thing. And lastly, f of x equaling x minus 3, where g of x equals the square root of x, and the bottom equals square root of x plus 6. When I plug in the x minus 3, I do end up with the same thing I got for j of x. So basically the solutions would be these four, whereas the other two would not be. They get close, they have some similarities, they have some of the same terms, but the location of where they are with respect to the radical is different, and therefore it makes it not the same function. Now, for me, sitting in on one of the recitations recently, I could tell that some of you had kind of already been working ahead and knowing the chain rule or have experienced the chain rule. But this composition of functions and decomposition of functions is kind of the centerpiece of what the chain rule is. And sometimes when you have more complicated functions where basically you have a function having the effect of another function upon it, it gets kind of tricky. Like, I mean, like for instance, right here, they give us x squared minus 5x plus 1 to the 10th power. You know, you could, as I said here, you could multiply that out and do like, you know, the distributive property that many times. But that would be like, you know, a much more complicated thing to do and would take up a significant amount of time to do that. Whereas we could find the derivative of this function by making use of the chain rule. So if I have a composite function f of g of x and I want to do its derivative, I would first do the derivative of, you know, and this is kind of what's different. Usually when we're doing the figuring out what a composite function is, we work our way from the inside out. When we're doing the chain rule, we're actually working our way from the outside in. So I would first do f prime of g of x, which basically means that, you know, I would basically be treating, in this case here, this x squared minus 5x plus 1 as if it were just a variable. You know, so I would apply the power rule to that and just like kind of treat that whole thing as a variable. And then I would do the derivative of g of x, which would be g prime of x, and then so I would work that on the inside. So as you'll see here, I believe that is what they actually do in the example. If I want to do the derivative of x squared minus 5x plus 1 to the 10th power, again, I'm going to treat this as a variable. So just like me having like the letter A or something there, or like just having an X there, if you want to think of it that way. And what I would do is I would say, okay, well, first I'm going to do, you know, they're kind of showing you the outside function, the inside function. So I'm going to do f prime of x would be 10x to the 9th. So I'm actually doing f prime of g of x, which would be 10 times g of x to the 9th power, which of course would be 10 times the x squared minus 5x plus 1 to the 9th power. And then I'm going to do the derivative of what's inside. And what's inside, you know, is x squared minus 5x plus 1. When I do its derivative, I get 2x minus 5. And they're going to show that right here. And so the overall function is going to be 10 times x squared minus 5x plus 1 to the 9th times 2x minus 5. Now, again, I could probably simplify this out using distributive property. Again, it would still be quite a bit to do with this one. That's still 9 of those I'm multiplying together. But, you know, if I need to evaluate things, this would be suitable and in many ways easier than me having to compute out all of that distributive property work and, you know, and have potential to make mistakes along the way. So that's how the chain rule works. Now it's your turn to give it a try yourself. So this is the function you were asked to differentiate. And to go along with this, another thing that the chain rule you need to make sure that you ensure that you do is that before you start working with it, you make it as simple as possible. If it is a situation that could easily be multiplied through, by all means do it. But you know, the fact that I have this expression 2x squared minus 3x plus 1 being squared and then cube rooted, I'm not going to be able to get it out from underneath the radical very easily. So, but instead of having it as 1 over all this and then have to apply the quotient rule along with the chain rule, I could just think of this function as being 2x squared minus 3x plus 1 to the negative 2/3 power. And then handling this becomes a lot more closely related to how we handled the example that I went through. So again, now I mean, if you want to rewrite it and say like, hey, well, I'm going to let f of x, you know, be x to the negative 2/3, and g of x be, the 2x squared minus 3x plus 1. I mean, you can certainly do that and then say, okay, well, if I do f prime of x, I'm going to, and do it that way. But I've gotten myself in the point where I just look at this when I do the first part of the chain rule, is that if this was just, I kind of just think of this as just being x. And that will save you some time, so you have to write out extra steps. I mean, for communication purposes, I mean, by all means, if this makes it easier for you, do it. And then show each step along the way. But as you're going to see as I do it, I do the negative 2/3, I keep all of this, and then I subtract 1 from this. And I subtract 1 from negative 2/3, I get negative 5/3. And then I do the derivative of what's inside here. And the derivative of that's going to be 4x minus 3. So my final answer is, and I'm going to erase all those extra marks I put on it, is going to be that function there. And there's really not much more I'm going to be able to do with it. I could possibly rewrite it a little bit because, I mean, generally, the way that most books write problems and present answers, if it starts off in radical form, then I'm going to tend to more often than not put it back into radical form. So, I'm going to have the negative sign. I'm going to have the 2 times the 4x minus 3 on top. I'm going to have 3 times the cube root of 2x squared minus 3x plus 1 to the 5 on the bottom. Because after all, the cube root of 2x squared minus 3x plus 1 to the 5th is the same thing as 2x squared minus 3x plus 1 to the 5/3. And having it in the bottom is what gets rid of the negative on the exponent. And although on the bottom I'm not going to be able to do any more, on the top I could simplify it further by distributing that too, because that's very doable. So, depending on the way the question's asked, if it says don't simplify, this would be a suitable answer. But taking it this far or this far might be something that would be more necessary should you have to do a second derivative of a function like this. It would be a little bit more easily handled than perhaps above there. But it's really, someone else's call, because I'd have to usually put it back in terms of powers anyway. So, and that's this problem. Let's move on to the next example. 2.6 also goes through what they call the generalized power rule. And it's really just applying the chain rule to a circumstance where I have some more complicated function other than just x being raised to a power, which is going to be oftentimes how we're going to make use of the chain rule early on. We will eventually have to use the chain rule when we start dealing with logarithms and other functions that we're going to deal with at a later time. But oftentimes you're not just going to be dealing with just using the power of a more complicated function. You might be doing a couple powers of more complicated functions being multiplied or divided. So this next example, I'm showing an instance where I'm going to be doing f prime of x, given that f of x equals 2x minus 1 to the 20th power times 3x plus 4 to the 15th power. Now again, to do 2x minus 1 to the 20th power would take some considerable time and create a very long expression that would be, very, clumsy to work with. And 3x plus 4, multiplied to itself 15 times would, give me a very similar type looking expression as well. Neither of which would be very easy to work with. And so this is an instance where the chain rule does come in handy, but you can also see that these two things are being multiplied together. So I will need to use the product rule as well. So when I set this up and start doing the derivative of f of x, I'm going to do f prime of x. I'm going to do first times derivative of the second, and I'm just showing the notation first, plus the derivative of the first times the second. So when I do the derivative now, when I start rewriting it again, now doing the derivatives, when I do the derivative of 3x plus 4 to the 15th, as you can see here, I get the 15 times 3x plus 4 to the 14th power. And then I do the derivative of what's inside here and get the times 3. And then I do the same thing when I do the derivative of 2x minus 1 to the 20th power. When I start doing the second part, I'm going to move the 20 down and get 20 times 2x minus 1 to the 19th power. And then I'm going to do the derivative of what's inside. The derivative of that's just going to be 2, so times 2, and then times the second function. Now I could do some simplifying here to, free it up a little bit, but I'm not going to be able to do a whole heck of a lot. I mean, I could do the 15 times the 3, I could do the 20 times the 2 here, and end up with 45 times the product of 2x minus 1 to the 20th and 3x plus 4 to the 14th, plus 40 times the product of 2x minus 1 to the 19th times 3x plus 4 to the 15th. If you had to do a second derivative, it might be a good idea to factor out the highest powers of these quantities you can to give yourself a simpler function to work with. But that would still, it's not going to create a whole big difference. The only thing it's going to really do is give you like, 3 multiplications together rather than having 2 sets of 2, either of which would be, involve complications to work with. But, doing a second derivative of these could be kind of time consuming, and you will have to do them from time to time. So it does take some, patience and to work at a, slow enough that you're not going to make mistakes and you can keep track of where you are in the derivative process. So as many intermediate steps as you need to write out as you do like more complicated things with these, the better. So, but now it's your turn to give it a try. And I'm going to ask you to differentiate the following. It's not quite as of a big circumstance as this one, and I'm going to ask it as multiple choice, but here you go. So you were asked to differentiate this, and you were given 4 choices to choose from. I'm just going to show you how to calculate the correct value and how the correct choice was obtained, because some simplification did happen. And most of it's stemming from the fact that, again, I have a circumstance where I'm starting with the square root symbol in the original function. And oftentimes, if that's the way it's presented in the beginning, that's the way it's going to be presented when it's over. You're going to put radicals back in. So I have f of x equaling x squared times the square root of x squared minus 1. There would be some people that would argue and say that I could just turn x squared into the 4th root of x to the 4th, or no, square root of x to the 4th, and then multiply that through. And that would be kind of a way to work around it, and I would think that it would produce the same results across the board. I don't think there's any x values I can think of immediately that would do that. But a lot of students forget that you could do stuff like that and probably would just go and do the method I'm about to show anyway. But before I got started with it, again, since I did start with the square root symbol, we don't really have a definitive rule for radicals. We do have a definitive rule for powers. I rewrote it as, well, I did kind of 2 steps here. I did rewrite this as, and I don't show it very clearly, is that I did rewrite the square root of x squared minus 1 as x squared minus 1 to the 1/2. And you can kind of see that here because you see me doing the product rule where I'm doing x squared times the derivative of x squared minus 1 to the 1/2 power plus the derivative of x squared times x squared minus 1 to the 1/2 power. So as I go through this now, I'm now going to carry through the derivatives where they're needed. So the derivative of x squared minus 1 to the 1/2 power, as we do the next step, as you can see, is going to be 1/2 x squared minus 1 to the negative 1/2 power. So basically, I kind of treated the x squared minus 1 as if it were just a variable. But now I'm going to do the derivative of what's inside there, and the derivative of x squared minus 1 is just 2x. So that takes care of my first times derivative second. And now I'm going to do derivative of first times second. So the derivative of x squared is just 2x. And I'm going to have that multiplied to x squared minus 1 to the 1/2 power. Now, I mean, some simplifying I can do at this point is realize that x squared minus 1 to the negative 1/2 power would be me doing the same thing as dividing by a square root of x squared minus 1. Of course, that would put it in the denominator along with this 2 and the 1/2. So the first term, well, as I see it, I'll see a 2x times an x squared. I would end up with, the division of 2 down here and the multiplication of 2 here do cancel. So I end up with x cubed times x squared minus 1 to the negative 1/2. And I'll eventually go another step in a moment and put that back in terms of a radical. I kept the second part pretty much the same because there wasn't much to simplify until I put the radicals back. And I would end up with x cubed over the square root of x squared minus 1 plus 2x times the square root of x squared minus 1 as the most typical answer that if a textbook were giving this in an answer key, that's the way they would probably present it. So, and that's the end of this one. If you have any questions, please, feel free to ask. Now, I'm doing two examples here because they're very closely related, and I want to kind of go through a couple of concepts before I give you a try at it yourself. And this is the notes basically that 2.7 covers, because 2.7 really only goes over one general concept, but it's a pretty lofty one and very involved, and that's dealing with differentiability. So they take a look at the function, the absolute value of x, and they have it defined up there. It is defined for all values of x, but we're going to show that it's not differentiable at x equals 0. And you notice it is it's a point there. And basically, if you have a corner point on a function, that's one of the instances where I'm going to have a function that's not differentiable. But we're going to show this by essentially using the definition of derivative. And that's really the only way that you're going to be able to do it, because one of the things that you'll note is that if you look it up, you're not going to be able to find a derivative rule for the absolute value function. And that's because of the fact that, the absolute value function is not differentiable at, in this case, x equals 0. If I have other functions that are related to it, it might not be differentiable at another point. But that's the whole idea, is that it's going to have at least one point where it's not going to be differentiable. And therefore, it's not going to have a steady rule for it. So they show you what it typically looks like, but here's how we go through the process of kind of like knowing whether or not it's differentiable at a certain point. So for showing a function to be differentiable or show it's not differentiable at a particular point is, basically a circumstance where I have to use the definition of a derivative. I mean, so that's another reason why they express it to you and they want you to learn, is because that's how I'm going to test this. So what you'll see here is that they're going to set up the, the limit of this. And so, as we go through this, I mean, and it's going to be kind of the explanation as to why there are no rules for differentiating the absolute value. So we want to show that this limit, and hence the derivative, does not exist at x equals 0. So when I do the limit of, and what's going on here is I'm instead of doing the the derivative of f of x, I'm doing the derivative of f of 0. So the x's are going to get replaced by zeros. The h's are going to be handled by the limit. So essentially what I have here in this case, now not every time you're going to test this out are you going to have the point being 0. A lot of them there will be, but sometimes you'll have another value there. We're going to look at finding the limit as h goes to 0 of f of h minus f of 0 over h, which is what the difference quotient becomes for that. So when I do that, I get the limit as h goes to 0 of absolute value of h minus 0 essentially over h, which means that we're looking for the limit as h goes to 0 of the absolute value of h over h. Now you cannot carry through the division because that top h is inside of a grouping symbol. and it's not a parenthesis. If it was just parentheses, which the basically the fraction bar would have taken the places of already, I just ignore it, just carry through the division. But an absolute value, I have to do something different and more involved to eliminate it. So for this limit to exist, the two one-sided limits must exist and have the same value. And that's where we get that, because and we're going to have this issue because of the fact of what the absolute value function does, because it does one thing for positive numbers and does another thing for negative numbers. So if I do the limit as h goes to 0 from the positive side of the absolute value of h over h, since h is positive in that instance, then the absolute values do absolutely nothing. And because of that, I would then be able to do the h divided by h. So I have the limit as h goes to 0 from the positive side of 1. Well, since there's no variables of h in there anymore, h has no effect on this. It's just going to stay 1. So I know that the left-handed limit, that I've established by using the definition of derivative becomes 1. When I do 0 approaching from the left, that means that the values of h are going to be from the negative side, and which means the absolute value is going to do the opposite of that, and it's going to do the negative of h, because the negative of a negative is a positive. And therefore, when I carry through the division, I'm going to do the limit as h goes to 0 from the left-hand side of -1, and that becomes -1. So we have the left-hand limit becoming 1 and the right-hand limit becoming -1. So since those two limits do not agree with each other, the limit of as h goes to 0 of absolute value of h over h does not exist. So, and since that was what we got from like simplifying the derivative of that, the derivative does not exist. So this is what we wanted to show, and that's how we show that it's not differentiable at that point where x equals 0. So, so there's ways you could tell, by looking at a graph if it's going to be differentiable or not. But ultimately you're going to be asked to determine if it's differentiable or not by using the definition, the limit definition of a derivative. So other non-differentiable functions. Here, any kind of corner point, anytime you have a sharp point, if it's a smooth curve, it does something along the lines of this, like polynomials do. Those are going to be differentiable throughout. But if I had to go from something that's following one nice pattern, and all of a sudden, oh, nope, go do this now, that corner point is going to be a place where it's not going to be differentiable. That's because another reason why, from a geometric standpoint, I could draw plenty of lines, several, that will only intersect that graph at one point. So all of those would be tangents. Well, how can I have multiple tangents for the derivative to exist? A derivative is a function. So, one value of x should produce exactly one slope for a line that's tangent to it. Well, if I have multiple lines that could be tangent to it, I don't have a function. So another instance is if I have a vertical tangent line. And this happens like dealing with your cube root functions, anything that kind of relates to these, you would see that kind of a line of a tangency somewhere, even if it's just something like along the lines of x plus 3. Although in that instance, it's not going to be at x equals 0. It's going to be at x equals -3 where you see that. And sometimes, like just with a square root function, you would see this. Your graph would only look something like this for it, because there's some values of x that are just not going to work. You would still have a vertical tangent at that one point, and also the fact that it starts and there's actually undefined values of x. Or values of x that make the function undefined. That's another sign that you're going to possibly have a non-differentiability there. And of course, the other big one is if you have a function that has a jump, or what we call a break. So basically, if it's discontinuous, and we've talked about continuity. I haven't given you many examples on continuity because I wanted to wait till we got to this issue because continuity plays a role in it. If I can prove that a function is discontinuous, it's automatically not going to be differentiable at that same point, But on the same token, just keep in mind that if I prove it is continuous, that's not necessarily enough to prove it's differentiable at a point, because after all, when I look at an absolute value function, like if it's doing something along the line of this, oh, this function is continuous everywhere, and even here at this point, which I'll call A, but because there's a corner point there, it's not going to be differentiable there. So discontinuity will automatically prove non-differentiability, but being continuous does not make it automatically differentiable. So to sum up our observations from the last, couple of slides talking about non-differentiable circumstances, basically, if I want to prove that, it's differentiable at a certain value of x, then I have to basically show it does not meet any of these conditions. I have to show that it doesn't have a corner point there. And that's usually, I can usually show that with limits, because usually if I do have a corner point there, I'm going to have, the limit as h goes to 0 plus of the difference quotient not equal to the limit as h goes to 0 negative of the difference quotient. Generally. If it has a vertical tangent, typically what you're going to see is when you do that derivative of the difference quotient, you're going to see that you're going to have a number over 0. As soon as you see that, that's actually sufficient enough to state that, well, that means I'm going to have a vertical tangent, and therefore it's not differentiable there, because technically, if it's going to be infinity or negative infinity, that doesn't really exist. But if it's certainly undefined or, does not exist, well, it does not exist. So you'll be good there too. And here, if it's discontinuous, so basically all I would have to show, and sometimes I have to consider the fact that the limit as x approaches c of f of x, and that does not exist, that's going to be something that I have to look at too. Usually this is the issue, and you look for this and have to look for this if you have a piecewise function. It's really the only time that you have to do that. Now remember, things that have corner points are piecewise functions, but I can clearly see at that point it has a corner point if I was looking at a graph. So whereas, if I'm looking at just a piecewise function without a graph of it, I may not know there's a corner point there. So I have to keep that in mind as I try to, evaluate this. So now what you're going to be asked to do is to look at several functions and a particular value of x and tell me if it's differentiable there. So you're going to probably need to take a rather long pause to do that, and you should, and do your best to see whether or not they're differentiable. There are some functions that are differentiable at the point I'm giving you, and there's some that are not. So, and don't just go along the lines of thinking, oh, if it has an absolute value, automatically it's going to have that. No, it's not. If it's a piecewise function, it's automatically going to be not differentiable at a certain point. No, it's not. So, keep that in mind as you go through, this process of determining whether or not they're differentiable, and then I will demonstrate, how I went about doing it myself. So, here's your example. Okay, you're back, and I'm hoping that it's been some time before you, or it's been some time between the time that you stopped listening to me in this recording and you've taken time to do these problems. So you were asked which of the following are functions that are differentiable at the indicated value of x, and you were given 6 functions to look at. I'm taking each one at a time because I'm just going to need the room to show it, and you should have given yourself enough room to work it out yourself. Now here, I'm going to do, I want to figure out, okay, and this is the absolute value of x minus 3 at x equals 3. Now, I mean, if you draw a graph, you would see at x equals 3, this particular graph, that's where the corner point would be. So, is it differentiable there? No, but let's use the limits to show that. So, f prime of 3. Now, if I find that f prime of 3 exists, I found the derivative there, therefore it exists there, that's good. And I'm only going to really be testing the one place where, I see evidence to suggest there could be a possible issue, If I see there's a possible break, or if I see there's a possible corner point, or I do see there might be some possibility of having a vertical asymptote, I want to prove that is the case. That's what I'm trying to do. So if I'm doing f prime of 3, that's going to be the limit as h goes to 0 of f of 3 plus h minus f of 3 all over h. So I go to the function and replace in the first one x with a 3 plus h, and then for f of 3 I replace it with a 3. And what I end up with is, again, the absolute value of h minus 0 over h. The limit of that as h goes to 0. And I basically end up with the same circumstance I had in the example that I shown. And if I do the right-hand limit, I do get its 1. If I do the left-hand limit, I do get its negative 1. Therefore, this limit does not exist, and therefore it's not differentiable at x equals 3. Now, students sometimes make the mistake of saying, okay, well, then, if you're asked a question, you see an absolute value, and it's automatically going to be non-differentiable. That's not true. Now, looking at this one here, a lot of students will mistakenly state that this also would be not differentiable at the point given if you're not paying close attention to it. I mean, basically what's going on at this graph, I'll kind of illustrate up here. At negative 4 is where it's going to have its corner point, but here at 4, it's basically just a straight line at that point. So we do fully expect this to be differentiable at x equals 4. So as I carry this through to prove that, again, I'm going to define g prime of 4 as the limit as h goes to 0 of g of 4 plus h minus g of 4 all over h. Next, I'm going to, substitute correctly. And everywhere there's an x in the first, and g of x for 4 plus h, I'm going to replace it with the 4 plus h, and for g of 4, I'm going to replace it with the 4. And what I end up with is the absolute value of h plus 8 minus 8 all over h. The limit as h goes to 0. Now, because this is not where, as h goes to 0, whether I'm slightly above 0 or slightly below 0, it's not going to matter. If I add 8 to it, and if I'm close to 0, it's going to be a positive amount, okay? So when I evaluate this, I could just clear the absolute value. I mean, because if I do it from plus or from minus, I'm just going to clear the absolute value in both cases and get the exact same thing. So this limit does exist. Or I could just recognize the fact that if I'm close to 0, h plus 8 is going to be positive regardless. If it was close to negative, if h was approaching negative 8, on the other hand, then that would matter. That would determine what happens with the absolute value function. But here, since it's approaching 0, and anything close to 0, when I add 8 to it, it's going to be positive. So as a result, the left-hand and right-hand limit are going to both be 1. This limit equals 1. So the derivative at x equals 4 does exist, and it equals 1. The next function we wanted to show here, if it's differentiable at is h of x, which equals x to the 2/3 power at x equals 0. So as I go through this one, now note here, since we are using a lowercase h to represent the function, I'm going to use an uppercase h in the limit definition, just to keep things straight so I don't like mix up, one h for another, and that could sometimes happen. So the derivative of 0 at h is going to be the limit as capital H goes to 0 of 0 plus capital H to the 2/3 power minus 0 to the 2/3 power over h. Now as I go through that further and simplify, I get h to the 2/3 over h. The limit as h goes to 0. And basically, when I simplify even further yet, I get the limit as capital H goes to 0 of 1 over the cube root of capital H, which if I substitute into 0, I get 1 over 0. Now, at this point, I do have enough to say that it's sufficient to say for me to say that these do not exist. This derivative does not exist because I'm going to have a vertical asymptote there. I've already more or less proven that I'm going to have a vertical asymptote, so, or a vertical line as a tangent. So, but I mean, I should go a step further and show this as well. And one of the things is, like, infinity and negative infinity are two different results altogether. But when you're talking about slopes, infinity and negative infinity are the same thing. They both represent a vertical line, as far as slope goes. I mean, they're undefined quantities, whether it's positive undefined or negative undefined. It's going to translate into being vertical. I mean, so I mean, that's why, it's arguable if you have to actually do this extra step. It's always a good step to try to do it. But in any case, it doesn't exist, and I could say that h of x is not differentiable at x equals 0. So we've taken care of the situations where I can have corner points, and although this graph here, I mean, that technically I have a vertical tangent line, it would still look like a corner point as well. So you would have, like, even graphically, you would automatically suspect that it's not going to be, differentiable at that point. But the next one comes into, like, the situation for continuity and things. So, like, for instance, for the next one you were given was j of x equals 4x minus 10 if x is less than 2, and 2x plus 1 if x is greater than or equal to 2. We want to see if it's differentiable at x equals 2. And typically that's where you're going to want to test whether or not it's differentiable, because as you can see, the way that this piecewise function is defined, when x is approaching 2 and equaling 2, that's where I have a change in the equation I'm following, or the expression I'm using to evaluate what j of x is, and as a result, I could possibly have a break there. Now, if I have a break there, if it's not continuous, then it automatically makes it non-differentiable. I don't have to go through the limit definition. So anytime I have a piecewise function, the very first thing I should try out is to see whether or not it is differentiable there, or continuous there. So if I check for continuity, as x approaches 2, j of x equals, well, again, if I'm approaching from the left-hand side, I'm following the formula 4x minus 10. If I'm approaching from the right-hand side, I'm following the formula 2x plus 1. So if I approach from the right, the limit as x approaches 2 from the right-hand side of j of x is going to be the limit as x approaches 2 from the right-hand side of 2x plus 1. And as you can see there from the algebra done, that equals 5. When I approach from the left, I'm going to be following the formula 4x minus 10. So when I put the 2 into that, I get negative 2. So the left-hand limit and right-hand limit don't agree. That means that the limit as x approaches 2 of j of x itself does not exist. That tells me that j of x is not continuous at x equals 2, and that automatically means it's not differentiable at x equals 2. So whenever you're given a piecewise function, if you're asked to show differentiability, you really should just, first of all, check it and see if it's continuous. And that's usually a little easier than checking on differentiability. If you prove it's not continuous at that point, it's not going to be differentiable there either. Sorry if on the last few slides my mic was wonky. I had moved it out of the way because my wife had called in the middle of this recording process about 3 times, and I moved my microphone out of the way and brought it back. But I listened back to hear that you can still hear me, which is good. So now you hear me a lot more clearly on this one. So, but getting to this particular example right here, k of x equaling 4x minus 1 if x is less than or equal to 1, and 2x plus 1 if x is greater than 1. Again, we're looking to see if it's differentiable, and usually we're going to be checking to see at the potential break point, because if it goes from one formula to another, that's where I could potentially have a break. But even if it ends up being continuous there, that's where I'm also going to have a potential corner point, because it may go from, like, one slope to another. And I could kind of see that going on right here just by the lines, but we're going to go and double check all this. So I'm going to check for continuity first, because if I could prove it's not continuous, then I could just stop there and say, well, it's not differentiable as well. So I'm going to do the limit as x goes to 1 of k of x. It's just that I have to do it from the left-hand side and the right-hand side, because if I approach from the right-hand side, I'm using the formula 2x plus 1. And if I plug the 1 into that, I do get 3. So the limit of k of x as I approach 1 from the right-hand side is 3. When I do it from the left-hand side and I'm using the 4x minus 1 formula, as you can see, I do get the same thing. So this limit does exist. It's a limit as x goes to 1 of k of x does equal 3, which means it is continuous at x equals 1. Now that it's continuous at x equals 1, I need to now show that it's differentiable there, or see if it isn't. And again, because I mean, it's continuous, okay, just like the absolute value function, it's a piecewise function. It's continuous everywhere, except that when you get to the corner point, it's not differentiable there. It's differentiable anywhere else. So as we go through this now I'm going to try to check and see if is this differentiable. So we've proven that k of x is continuous at 1. As I said before, there's a potential break at x equals 1 now that I've already taken care of and said, well, it's not a break. However, since I do have two different formulas telling me how k of x is calculated, I can still have a corner point. So I want to see if I do in fact have a corner point. So now when I define k prime of 1, I'm going to be doing the limit as h goes to 0 of k of 1 plus h minus k of 1 over h. Now, the issue I have with this is that still, you know, I don't know which formula I'm going to be using, and it does matter which formula I use. If I'm looking at x values that are more than 1, I'm going to be using the bottom formula. And since 1 is still a point of contention in how I would calculate I used it to calculate the point of they do in fact meet up at x equals, at x equals 1 at the y value of 3. But I got to see what the slopes are doing on the left and right hand side now. So I'm still going to be testing this out for an instance when x is less than or equal to 1. So when I do k prime of 1 and use that difference quotient, I'm going to be doing the limit as h goes to 0 of 4 times 1 plus h minus 1 minus the quantity 4 times 1 minus 1. And as you can see from the algebra I show there, that simplifies to become 4. The limit as h goes to 0 of 4, which means it's k prime of 1 is 4. When I do values of x that are greater than 1, I'd be using the formula 2x plus 1 instead. So when I show the derivative using that formula, I do in fact get that the k prime of 1 equals 2. So when I have values that are smaller than or equal to 1, I have a slope of 4. So as I'm even right before, up until including 1, my slope is going to be 4. When I am approaching from the right-hand side, the slope of my tangent line is 2. So that means I do have the existence of a corner point. So that means that this does not exist, and that means that k of x is not differentiable at x equals 1. On to our last one. For our last example here, we have v of x equaling x minus 4 quantity squared plus 4 if x is less than 4, and negative x minus 4 quantity squared plus 2 if x is greater than or equal to 4. It is a piecewise function. I want to see if it's differentiable at x equals 4. Again, one of the issues is that at x equals 4 is where I have a potential for a break. So I want to determine at first if it's continuous there, and if it isn't, I'm not going to go any further because it wouldn't be differentiable there either. So I'm going to do the limit as x goes to 4 of v of x. When I approach from the left-hand side, I'm going to be using the top formula, so I'm going to be evaluating x minus 4 squared plus 2 equaling, as x approaches 4 from the minus side. So if I do that, I get 0 plus 2, which equals 2. If I'm approaching from the right-hand side, I'm going to be using negative quantity x minus 4 squared plus 2 which gives me negative 0 plus 2. Well, negative 0 is 0 still, so that's been plus 2 is still 2. So the left-hand and right-hand limits agree. The limit as x goes to 4 of v of x equals 2, which means it is continuous there. Now that it's continuous there, and I know it's continuous at x equals 4, now I'm going to see if it's differentiable there too. So I'm going to do the limit as h goes to 0 of v of 4 plus h minus v of 4 all over h. That's how I'm defining v prime of 4. Now the issue is, again, if I'm less than 4 or greater than or equal to 4, it's going to matter which formula I'm using. So I'm going to use the case that x is less than 4, which means that the derivative is going to be defined as the limit as h goes to 0 of 4 plus h minus 4 quantity squared plus 2 minus 2. And that gives me that v prime of 4 is going to be equal to 0. You can see all the algebra that happened there. So v prime of 4, the derivative at 4, if I'm using the formula for values of x that are less than 4, is going to be 0. If I'm approaching from the right and x is greater than or equal to 4, v prime of 4 is going to be defined as the limit as h goes to 0 of negative 4 plus h minus 4 quantity squared plus 2 minus 2. Again, I'm doing some distributive property stuff there, so you're aware of it. So I end up with v prime of 4 equaling the limit as h goes to 0 of negative h. But I plug the 0 in, I still get 0. So v prime of 4 is 0 when I use this formula as well. So I get the same value if I'm assuming x's are going to be less than 4 or if x's are greater than or equal to 4. So it doesn't matter which formula I'm using at 4 to come up with a derivative, it exists. It equals 0. And since it exists, v of x is differentiable at x equals 4, and v prime of 4 does equal 0. So as far as the answers I had, the ones that are differentiable are g of x and v of x. The others were not. If you have any further questions, please feel free to contact me or ask about it in class. Thank you and have a good day.